Okay, so good morning everyone. So we are looking at this problem. So the problem that we want to solve is division in uh, okay, uniform NC1, and as I said, so this is a result due to Cook, Beam and Hoover. Okay. So what we have seen so far is, so last time we saw that suppose if we want to compute iterated product. Okay. So we have already seen that we can reduce division to the problem of computing iterated product, and in fact we can reduce division to the problem of powering, and powering is just a special case of iterated product. So our target is to show that we can compute iterated product in uniform NC1. So what have we seen so far? We have seen that we can compute iterated product modulo a prime power, a small prime power in uniform NC1. That is something that we have seen. And another result that we saw last time is that this Chinese remaindering theorem. So we saw that Chinese remaindering theorem can be reduced to the problem of computing iterated product. Okay. So that is what we have seen so far. So essentially what it boils down to is how do we solve iterated product. Okay. So that is what we are going to focus on today, and we will complete the proof of this theorem. So before getting into the result that we will be proving, let me start with a definition. So we will define something called a good modulus sequence. Okay. So a good modulus sequence is a sequence M1, M2, so on, such that Mn has two properties. Mn is at least 2 raised to the power n and at most 2 to the power n to the power d for some d greater than or equal to 1, and the second property is that for all prime powers such that p raised to the power l divides Mn and p raised to the power l plus 1 does not divide Mn, p raised to the power l is at most r of n for some polynomial Rn. Okay. So basically a sequence is a good modulus sequence if there exist two things. One is there exists a constant d greater than 1, another is there is some polynomial Rn such that the nth value of the sequence Mn is between 2 to the power n and 2 to the power n to the power d, and every prime power that divides Mn is small in some sense. Okay. It is bounded by the polynomial R of n. Okay. So it is not too large. So one thing, if you just d is a constant, t does not depend on n, it can be any constant. Okay. So, yeah. Let me write it over here, some constant d greater than or equal to 1. Okay. Now, I mean, if you just look at this, so d equal to 1 actually will not work, because if I set d equal to 1, it means that m of n is exactly equal to 2 to the power n, and 2 to the power n, the only factors of 2 to the power n is 2, the only prime factor, and the highest prime factor is 2 to the power n itself, and 2 to the power n is of course bigger than any polynomial. So, d equal to 1 does not work. So, I mean, without any loss of generality I can remove this, but yeah, I mean, d equal to 2, 3, I mean, they might work. In fact, we will see. So, let me give some examples. So, some examples. So, one example is Mn is the product of first n primes. Okay. So, if you look at the first n primes, you can show that it lies between, it is greater than 2 to the power n, and it is less than actually 2 to the power n square. Okay. And of course, the product of the first n primes, the only prime divisors are the prime itself, and the nth prime by the prime number theorem is at most n log n. Another example is Mn is defined as the how I write it. So, the product of the elements in this set p raised to the power l such that n is between p raised to the power l and let us say p raised to the power l plus 1. Okay. So, for every n, look at the highest prime power that is less than or equal to n, okay, and take a product of all these prime powers. So, this also can be shown to be a good modular sequence. Okay. But anyway, so this is just aside. So, now what we will show today is the following theorem, that computing iterated product NC1 reduces to the problem of computing a good modulus sequence. Okay. So, let us see the proof of this. So, we want to compute iterated product. So, we are given x1 up to xn, and we want to compute so we need to compute this term, right, given x1 through xn. So, what we will do first is we will use the oracle to get the value of m n square. So, we know what n is the number of inputs. So, whatever oracle we have for this good modular sequence, we use it to get the value of m of n square. Now, okay. Next, what we will do is we will factor m n square. Okay. Factor m n square into prime powers, let us say P1 to the power L1 so on up to Ps to the power Ls, okay. And let us say I set C1 as, or I will set Ci as Pi raised to the power Li. For I between 1 and s. So, we just factor all of these, and what we are guaranteed is that all these prime powers are bounded by a polynomial. Okay. So, these prime powers are small. So, therefore, we can do this factorization easily by a log depth circuit. So, this we have also seen last time that yeah. So, if I have a number which is bounded by a polynomial, then I can factor it in log depth. Okay. So, next, so essentially what we are going towards is we will actually use Chinese remandering. Okay. So, we will show that we can use Chinese remandering to get the product pi xi. Okay. Now, note one thing. So, what is product of xi? Okay. Okay. So, before getting into that, so let some number. So, we have an oracle, right. So, we are showing we will reduce it to the problem of computing a good modular sequence. So, there is an oracle which given n outputs mn, correct? Huh? Mn is some number, yeah. So, given n it outputs mn. So, I give it n square, it will output mn square. Okay. So, I give the oracle n square and it will, this is going to output. So, what do we know about this mn square? Okay. So, let us write a small note here. How large is mn square? So, by the definition of good modular sequence, mn is greater than 2 to the power n. So, therefore, mn square is greater than or equal to 2 to the power n square, right. And what can I say about the value of product of xi? How large can a single xi be? Hmm? 2 to the n, it is an n bit number. So, it can be as large as 2 to the power n. There are n of them that I am multiplying. So, how large can the product be? So, the product is again at most, actually it is n bits, so it is 2 to the power n minus 1, but whatever. So, it is 2 to the power n square, right. So, this is strictly greater than the product of xi, right. So, basically this term that I am factoring, okay, is bigger than the product. Okay. In other words, the product is bounded by this thing. Okay. So, now what we will do is we will compute, let us call it B, B of j, which is equal to product of xi, I going from 1 up to n modulo Cj, okay, once again for I between 1 and s. Okay. So, again this is something that we have seen, that if I am computing the product modulo a small number, a polynomial, then we can do this in NC1. This is something that we have seen. So, using that algorithm we compute Bj. Okay. Now, what happens if I use Chinese remandering? Okay. So, recall what the Chinese remandering problem was. The Chinese remandering problem was that given n relatively co-prime numbers C1 up to Cn, okay, and given some xi up to xn such that these xi's are smaller than ci's, okay, there exists a unique x. Okay, so this is the Chinese remainder theorem that I mentioned. There exists a unique x which is less than the product of these Ci's, and this x satisfies the property that x mod Cj is equal to xi. Okay. That is what we x mod Ci is equal to xi. That is what we saw last time, and we saw an algorithm which actually allows us to compute this number, okay, given the product. Now, what we will do is that, so in our case, so these Ci's will be the same Ci's of the Chinese remaindering theorem that we had, and the Bi's will be our Xi's. Okay. So, use Chinese remaindering theorem to get. So, what does Chinese remaindering output? It outputs this number x, right. So, let me, for the time being, let me just call it as capital X, okay. So, to get x given these C whatever Ci's and Bi's. So, what property does x have? Okay. So, note that what is the product of these Ci's in our case? So, the product of these Ci's is mn square, okay, and mn square is greater than or equal to product of xi. Okay. So, what I am alluding towards is that this quantity is actually a solution to the Chinese remaindering problem, product of xi. Okay. So, one solution to this problem is the product of xi. Why is that? Okay. So, one more condition that we need for Chinese remaindering is that these Bi's are less than or equal to Ci's, which is actually clear because I am taking modulus. Okay. So, I can write it over here. I will come to that. So, I will come to that. Okay. So, this Bj is less than or equal to Cj by definition. Now, what we have is, of course, that product of xi is less than product of this Ci. So, this is actually I going from 1 to, write it as j, I going from 1 to So, product of xi is greater is less than mn square. Okay. So, product of xi and mn square is equal to product of Cj. So, therefore, j going from 1 up to s, therefore, product of xi is less than this product, correct. So, this is one condition that is satisfied. Now, what is the second condition? The second condition is that this number product of xi that we have, I going from 1 to n, mod Cj should be equal to the Bj, okay, for all j between 1 and s. That is also satisfied by the way I computed Bj itself. Okay. Therefore, this is a solution. Correct. And by the Chinese remaindering theorem, we know that there exists a unique solution. Okay. So, the moment I apply Chinese remainder and I get x, what I have is, by the Chinese remaindering theorem, this capital X that the algorithm outputs is exactly equal to product of xi, and we get our answer. Clear? So, what was the idea here? The idea here basically was twofold, actually three things. One is that I am computing a number which is like bigger than the product, and it has the property that every factor, every prime factor, or every power of a prime, or every prime power that divides n square is small, which allows us to factor it efficiently. That is the second thing. And the third thing is the way I design my BJs. Okay, so the way I design my BJs, it becomes exactly equal to what I want finally. Okay, so I define my BJs to be the product modulo CJs. Okay, so therefore the only solution that this input will have is x equal to product of xi. Okay. So what are we left with? So essentially we are left with how do we get this mn square. Okay, so here I assume this as an oracle, given n, how do I get mn square. So and now note that I am not using any particular modulus sequence. This actually works for any good modulus sequence. I have not used a specific fact, and we have seen here some modulus sequences. Okay, so in particular I will take the first one. Okay, so the last part is actually easy. So given n, computing mn square is actually in P. Okay, so we will use polynomial time algorithm over here. In fact, there are actually better algorithms. There are actually ways in which it can be done even in log space, but it is enough. So what we will show, or what actually Cook, Beam, Hoover showed, is that this is a P uniform NC1 reduction. So compute the first n square primes and compute their product. Okay. So quickly let us see why this is a good modulus sequence. So the mn square that we get as a result of this, okay. So what is the product of the first n square primes? Okay. So the product of the first n square primes will be product of, or I mean I do not even need to say this for, I have to show it is a good modulus sequence, so I will just argue for mn. So mn is product of pi, I going from 1 to n, where pi is the ith prime, and what we know by prime number theorem is that pi is at most some C I log I. Okay. So therefore, I mean let us say it is I square, I mean I log I is of course less than I square. So I can write product of pi's as product of I whole square, I going from 1 to n. So this is n factorial whole square, and well, n factorial is of course less than or equal to n to the power n. N to the power n can be written as 2 to the power n log n. So again, so this is basically less than 2 to the power 2n log n, which is like less than 2 to the power n square. Okay. So we have by the prime number theorem that mn is less than 2 to the power n square. So one condition is satisfied. Of course, each prime is at least 2. Okay. So therefore mn is greater than 2 to the power n. Okay. So the other condition is also satisfied, and by the prime number theorem, once again the only factors are the primes, each prime is bounded by n log n. N log n is of course a polynomial, so it is satisfying the next condition also. Okay. So, this is basically showing that the first n primes is computing the first n primes is gives us a good modular sequence. And now essentially what we are doing is we are doing this in polynomial time. So, that is, and that does not matter for us because here, so where are we using? So, here we are using this algorithm to compute mn square, right, and well, this is actually independent of my xi's, right. So, this is independent of my xi. So, I have to compute a circuit for, so which works for all inputs of length n. So, there I just I actually do not get log space uniformity, what I get is p uniformity, right. So, basically where did I write the reduction? Huh. Hmm?
How we are getting the oracle then? Does that determine what kind of reduction?
No, the oracle we do not care how we get the oracle. The oracle.
This P thing you are telling, this is about how we are getting the oracle.
Correct, but now think of the circuit. So, what I am saying is that I actually do not need any circuit to compute mn square. So, given n, I will just do some pre-computation and I will get the value of mn square, okay, and that mn square actually works for all inputs of length n, right. So, I have to kind of show the existence of a circuit, right. So, the answer that we get is, so here I purposefully did not write what kind of uniformity. So, what I get is that division is in P uniform NC1 as a result of this. So, given n, first, so you can think of it like this. So, given these x1 to xn, I do not look at the input, I look at n, I apply a polynomial time algorithm, I get mn square and then everything else follows in place. Okay. But again, so as I said that there have been works after this which have improved this P uniformity to even log space uniformity, but we will not get into that. So, this completes the proof for us. Okay. So, any questions? So, now we will also look at, in fact I will not get into the proof of this, I will leave some of it as exercise, but we will look at one more reduction that I said at the beginning. So, if you recall at the beginning of this topic we looked at 3 problems, we looked at division, we looked at powering and we looked at iterated product. So, we saw that division and powering are NC1 equivalent, right. So, division reduces to powering and powering reduces to division, and what we have seen here is that powering reduces to computing iterated product. Well, powering reduces to iterated product is actually easy. So, we have seen that. So, the next result that we will see is that iterated product NC1 reduces to powering, right. So, actually these 3 problems are NC1 equivalent, all 3 of them, and this is actually not very difficult, I mean some 2-3 small ingredients. So, what is the iterated product problem? So, we want to compute product of these xi's. So, what we will do is we will set let x be equal to the number 2 to the power 2n plus 1, okay. So, given n I can of course compute this, given n I can get 2n and 2 to the power 2n is just adding 2n many zeros. Next, use powering to compute the number 2 to the power I think x square, right? What do I need here? We will compute x raised to 2n. So, let us call this as y, and now what we will show is that, so this y that we have, okay. So, if we look at the following bits of y, okay. So, the how do I write this? Bits of y from position 2n square to 2n square plus 2n minus 1, okay, is exactly equal to the binomial, well, it is equal to 2n choose n, okay. So, essentially what I am saying is that if you look at y, okay. So, let us say I look at this y, okay. So, I have my bits of y. So, let us say it is some y t minus 1 up to y 0 I have. Now, look at the position y of 2n square up to y 2n square plus 2n minus 1. So, this term is exactly equal to 2n choose n, okay. Now, why we have 2n choose n, I will just come to a moment, but just let us first observe that we can get y, okay. So, if I can actually do powering, I can compute x raised to the power 2n and I can get y, and I can of course select these many terms from y. Now, why is this important? What is special about 2n choose n? So, 2n choose n is actually a good modular sequence, okay. So, I will just leave the remaining as an exercise. So, what you can see is that show that Mn equal to 2n choose n is a good modular sequence. And what we have seen just earlier is that if somebody gives me a good modular sequence, I can compute iterated product, okay. So, 4 is using the value of 2n choose n, get iterated product as earlier, okay. So, the only part that remains is to prove this is this is a good modular sequence, and that you can figure out, right. So, basically there are 3 things that you have to show. You have to show that Mn is greater than 2 to the power n, it is less than or equal to 2 to the power n to the power d for some d. So, you have to come up with a d, and you have to show that the only factors of Mn are the only prime powers that divide Mn are bounded by a polynomial. Okay. So, that is it. any questions. Okay, so let's move. Which one? So how many bits will this have? Okay, so if you look at x, x has 2n many bits, correct? So x has 2n many bits. So if I have 2n bits, raised to the power log n will give me how many bits? So it will be some 2n into log n many bits, right? So I have that many bits in y, 2n into log n, because I mean n has log n many bits, right? Okay, so it is 2n, right? So it will be 2n into 2n, yeah. So y will have actually about n square many bits, 2 to the power 4n square many bits. So there I am looking at the bits from position 2n square up to position 2n square plus 2n minus 1 in that string. Mm-hmm. 2n square, right. Oh yeah. This would be 2n square to 2n square plus 2n, correct. Yeah. I don't even have that many positions. Yeah, here it is correctly written, here it was incorrect. Okay. Anything else? Okay, so let's move to something else now. So we have seen these classes, right? So we have seen these classes NC. Okay, so let me just write what I want to discuss next. So we will look at the relation between bounded depth circuit classes and other uniform complexity classes. Okay. So we have seen these classes NCI, ACI and so on, and we have also seen the following results. So we have seen that, well, NCI is of course contained in NC I plus 1, ACI is contained in ACI plus 1, NCI is contained in ACI, and ACI is contained in NC I plus 1. Okay. So the first three are actually definition, it follows directly from definition. The fourth one just follows, I can take every gate of unbounded fan-in and I can replace it with a log depth circuit of bounded fan-in. Okay. So that gives me the fourth one. Now what are the relationships, what relation do we know between these classes and other uniform classes? By uniform classes I mean classes such as P, maybe NP, or maybe some smaller classes. Okay. So let me define these space bounded classes. So again, if you have had some exposure to complexity, you would know these classes, but for the sake of completeness I will just define them. So L is the class of decidable by a deterministic Turing machine in log space. Similarly, we have NL, which is a class of languages decidable by a non-deterministic Turing running in log space. Okay. And some of the known results that we have in this area are that, well, L is contained in NL, NL is contained in P, of course, P is in NP. Okay. And one more result that we will be using, again this is a well known result, that directed graph reachability is complete for the class NL. Okay. So, as I said that these are some of the results which are taught in any basic complexity course or even in a theory of computation course, and I am going to assume that you are familiar with these results, but even if not, I mean you can just take them as granted and we can move on. This is something that can easily be looked up. Okay. So, what we will prove is the following, that where does these classes sit with respect to these classes. Okay. So, what is the relation between these bounded depth classes with respect to these uniform complexity classes. So, I will come to that. Okay. So, the theorem that we will be proving is that uniform NC1 is in L and NL is in uniform AC1. Okay. And when I say uniform, what I mean here is log space uniform. Okay. So, yeah. So, how does the proof go? So, to show that uniform NC1 is in L, what I have to show is that given a circuit, okay, so basically if I am given a circuit, well, I am not just given a circuit, but I am what I am given is a log space machine, okay, which given n can actually produce that circuit. Okay. So, given such a machine, so therefore, I can assume that I have this circuit. What I will show is that given any input to that circuit, there is some other log space machine which can actually decide whether that input belongs to that language or not. Huh?
If a log space machine can generate these circuits, then isn't it by default that a log space machine can compute such a log?
Yeah. But I mean, what about a specific input? So, it is generating the circuit, but now given an input, that input, I mean there are 2 to the power n inputs of that same length. Now, how do you know that which input lies in the language and which does not? Okay. So, what we will show is that any NC1 circuit can be simulated in L. Okay. So, what is the idea? How would you go about doing this? So, let us look at a pictorial proof first, and actually it is quite easy. So, we have this circuit C and we know that it has depth some order log n. How can I simulate this in L? Okay. So, essentially what we do is we do a DFS of this circuit. We start at the output gate, okay, and then we do a DFS. So, what I am doing in the DFS, so at every step of the DFS, whenever I come to a node, first I will explore its left subtree. I will try to compute whatever is the output of the left subtree. Okay. Then I will take that, I will store that one bit, whether it is the output is 0 or the output is 1. Then I go to the right subtree, I compute the value of the right subtree. Now, I have already stored the value computed by the left subtree. So, I will use these two values, and depending on whether that gate is a AND gate or a OR gate, I will compute its output value. Okay. So, because otherwise, so if let us say I do not call this as uniform, okay. So, I will come to that, okay. So, that is a good question, I will come to that. Let me just complete this discussion and we will come to that. Okay. So, let us look at the algorithm. The algorithm is, as I said, quite simple. So, do a DFS of C starting at the output gate, and what do I do in the DFS? At every gate, what you do is recursively, or you do not have to even have a recursive algorithm, you can design an iterative algorithm for this. At every gate, compute the value outputted by the left subtree, okay, and store it, then similarly compute the value of the right subtree. Now, using these two values, compute the value at the current gate. Okay. So, essentially observe what are the things that we are storing. At any gate, essentially what we have stored is the path that I have taken to reach that gate. What is a path? A path is just a sequence of left and right. Okay. So, from the parent, which edge am I choosing to go to the next child? Okay. Or we can think of it as follows, that from a node, whether I came from a right parent or a left parent or whatever, I mean you can assume without loss of generality that there are two output gates, but essentially at every step I will be keeping track of at any gate, let us say G over here, I will keep track of the path to reach that gate. Okay. This is a sequence of left and right, and let us say if I am going right at some position, which means that I have already explored the left, which means that in addition to that r bit that I am storing, I will also be storing one value, whether it is a 0 or 1 that I had pre-computed earlier. Okay. So, essentially some 2 bits I need to store along this path, and the total depth of this path is log n. So, I will be storing some log n bits. Okay. And once I have done this, when I have completed DFS, I would have gotten the value at the output gate. Okay. So, this is simple. Now, the question is why uniform NC1? So, why we need uniform NC1, that is actually quite clear if you just think for a bit. So, essentially what do I mean? So, when I say uniform NC1 is in L, what do I need to show? I have to show that every language which belongs to this set, for every language which belongs to this set, there is a log space algorithm for that language. Okay. So, let us take a language, because I have L over here, let me take a language M. Okay. So, suppose M belongs to, okay, let us say not uniform NC1, but let us say suppose N belongs to NC1. Which means there exists a circuit family for M, right. Now, given an input, okay, so let us say I am given an input x and I want, so basically now for M I have to design a log space machine, which means that given any x, this log space machine should output whether to accept or reject on x, right. Now, given an x, of course I know the length of x, but what is that circuit? What is the circuit C of n for that x? Or for that input length? I do not know that circuit, and NC1 does not say anything about how that circuit can be obtained, it just says existence of that circuit, right. So, unless I am given some uniformity condition, there is no way of getting it. Now, suppose if I am given that, okay, so suppose M is in NC1, then there is no guarantee on how C of n the nth circuit Cn can be obtained. Okay. On the other hand, suppose that M was in L uniform NC1. So, L uniform is just a shorthand notation for log space uniform NC1. Then what I can do is that given any x, I compute what is the length of x. Now, let us say that length be n. Now, I know that there is a log space machine which when given n can produce Cn for me. Now, I get Cn. Now, I run this simulator for Cn which gives me a log space algorithm, and using that log space algorithm I just say yes or no for that x. Okay. So, that is why this uniformity is very important over here. Without this uniformity you cannot prove this. Exactly. Okay. That is the next thing that I was going to say, that you can actually show that if you are given yeah, so even NC1 can have undecidable languages. So, how do you prove that? How do you prove NC1 will have undecidable languages?
One example is to encode the vaulting code or any undecidable problem in unary.
Precisely. Okay. So, take any undecidable problem. Okay. Now, you encode it in unary, okay, which means that for any input length, okay, so that encodes, let us say any n basically encodes an instance of the halting problem. So, now for every n, either that n belongs to the language or it does not belong to the language. Now, in unary there is a unique string of every length, right. So, either that string belongs to that language or does not belong to that language. Okay. Now, given a string, there is very easy to say that, I mean, it is very easy to design a circuit Cn which will accept that string. Okay. You just take a, well, whatever and or of all the proper literals, okay. Because now Cn that we want has to accept only one string, okay. How we get Cn we do not care, okay. So, there always exists a Cn which would output a, which would accept a unary language, okay. So, I will, yeah, I will not get into this, I will just mention this as a note that NC1 contains undecidable, in fact not just NC1, I mean, okay, fine, and any non-uniform, well, not any, you have to look at the entire input. So, for example, NC0 will not work, in NC0 you can't even look at the entire input.
Yeah, but still it can have undecidable languages, like we can.
No, but how do you, if you do not look at the entire input, see you have to encode the entire input, right. So, you have x1 up to xn.
Yes, but we can just random. I mean, intuitively, like we can see. Suppose I can say that okay, I am going in the for the first case, I am going to see only the first bit. For the second, I am going to see the fifth bit, and like this, I can like for any n, I can have random such bits. So basically, like it can be undecidable. Even for NC0. Because
But what about the bits that you are not looking at?
yeah, but we don't care about it. Like, I mean, for example, for any length of the input, I see
There is exactly one binary string which is accepted. Now, if you are ignoring some input bits, you are actually increasing that set, binary set. Okay. So, what do you do on those? So, for example, if you are, let us say not looking at x2, no, you have to accept or reject, right, you have to do something. If you accept that binary string, I can actually have, let us say, some setting where it should have been rejected, and if you reject, I can create a setting where it should have been accepted. So, because let us say, let us look at any binary string, right. So, let us look at, okay, let us take an example. Okay. So, let us say I have the binary string for n equal to 4, this 1011 should be accepted, all other binary strings should be rejected, right. Now, how do you accept this string? By looking at, let us say, only 2 bits.
No, I am saying, for example, if I say that for a 4, for the length 4, I will see whether the second bit is 0 or 1. If the second bit is 0, I will accept, and if the second bit is 1, I will reject. So this is my definition for the circuit of.
So, if the second bit is 0, you will accept, then you are going to accept this also, but this should have been rejected.
So, like this is not my definition. I am just saying that this is a I am constructing a.
So, that is what I am saying. So, you are the circuit that you are constructing is not correct, because it is also accepting extra strings.
So how to language is different with
Huh?
trying to give the same a construction for the same language. He's trying to construct a different language.
Yes, but you have to do it for the same language here. What you are constructing is actually accepting a different language.
No, I am saying that we can construct undecidable languages like this.
But then you have to prove that that language is also undecidable, the one that you are constructing.
No, but I think that I think that proofs can exist.
So, I am not sure actually, when you say NC0, it means that you can only look at constantly many bits of the input.
So even if I look at one bit, so for example, I can like which bit to look at, I can decide that with the.
Yes, you can decide which bit to look at.
Yeah. So, but that which bit to look at, if it is, for example, if I say that for length for n equals to 0, I mean for the nth, if the the input is of length n, I will look at the nth bit, for example. This means the way that thing is coming. For example, we see Cantor's diagonalization argument that for infinite strings that like anything can come, like we can select such a string where we can't just compute the nth bit, like there is no algorithm to compute the nth bit, so uncomputable numbers basically. So if I select such some uncomputable number and I say that we are taking the digits of the bits of those uncomputable numbers, then we can have the existence, we can show basically the existence of such NC0 in classes with undecidable factors.
Yeah, not. So essentially what you are saying is that even so each and every computing each and every bit is undecidable. So there exists a sequence where every bit computing every bit is undecidable. So if you can get the value of even one bit, it makes it decidable. That is what you are saying in some sense. I am not sure, so that needs a proof actually, how you prove it, but maybe yeah.
Like for example, we can take an uncomputable number. So there are computable numbers and uncomputable numbers. Now uncomputable numbers also have an infinite binary representation, and we say that each time we look at the either the 0th bit or 1th bit, depending on like what is the bit in that uncomputable number. So that kind of a circuit exists, but we can't compute
Yeah.
with that circuit.
Yeah.
Not circuit exists, the family of circuit exists.
Yeah, family exists. So basically, so Ci kind of gives you what that ith bit is of that. So if there exists a circuit, then you can compute it. Yeah, yeah, you are right. Yeah, maybe yeah, you can show that. Yeah, that is true. Yeah, so then even NC not just NC0, even like getting one bit, so which is even smaller than NC0 in some sense. It's just a projection. So yeah. Anyway, let me just. Yeah, and in all these things, what is crucially used is the non-uniformity of the class. Right? Okay, so now coming to the next thing, that is how to show NL is in uniform NC1, uniform AC1. So how do you argue that? So we have to argue that every problem in NL, for every problem in NL, there is a AC1 circuit. So here we will use the fact that NL has a complete problem, and what we will show is that graph reachability is in uniform AC1. Okay. So to prove this, let me define a predicate. So what is the graph reachability problem? So the graph reachability problem is the following. So it's a tuple given G, S and T. It should accept if there is a path from S to T in G, and if there is no path, you reject. So that's the graph reachability problem. So I define a predicate reach U V I. Okay. So this is equal to 1 if there exists a path from U to V of length at most 2 to the power I, okay, and it is equal to 0 otherwise. Okay. Now how can you show? So now we will argue that we can actually, given UVI, I can actually compute this predicate in AC1. How would you do that? So essentially I have to give a log depth circuit, but now I am allowed unbounded fan-in.
Recursively compute reach UWI
exactly. So, what is that idea? So, what is the theorem? Huh? So, Savage's theorem, exactly. So, this is basically just another way of looking at Savage's theorem. Okay. So, reach UVI is true if and only if there exists a vertex W such that reach U W I minus 1 is true and reach W V I minus 1 is true. Okay. Because essentially what this is saying is that, well, if I have a path from U to V of length at most 2 to the power I, then there is some middle point in this path, right, some point W in this path. And what property does the middle point have? That this length is at most 2 to the power I minus 1 and the other part is also at most 2 to the power I minus 1, right. So, and now it is easy to see how we can compute this circuit. So, here is a circuit for reach. So, how do you do the circuit? So, we can write essentially just encoding this. So, reach U V I is equal to, I take a OR over all W in G reach U W I minus 1 and reach W V I minus 1. Okay. So, basically, and finally what do I have to compute? What would the output gate be? What is, huh? Huh? No, it will be an AND gate, but which gate? I mean, what is the predicate at the output gate? Exactly. So, what we need to compute is reach of S T and log n. Why log n? So, n is the number of vertices. So, any graph, I mean the maximum length path in any graph is at most n minus 1, which is 2 to the power, which is less than 2 to the power log n. So, if I can actually compute this predicate, then I have an answer to reachability, and basically to compute this predicate, what I have shown is that it reduces to computing reach of whatever this for lower values of I. Okay. So, in each level we have 2 layers of gate. So, I have a unbounded fan-in OR gate and then I have a AND gate with fan-in 2, okay, and the number of such levels is log n, because if I is equal to 0, then I can just look at the adjacency matrix of the graph and I can answer whether there is a edge or not. Okay, if I equal to 0 means 2 to the power 0 is 1, so it is just checking for an edge. Okay. Huh? OR, this OR has this many gates, right. So, this circuit has OR gates with unbounded fan-in and AND gates of, in fact, fan-in 2. Okay. So, this is actually, so there is a name for this class as well. So, of course, this is in AC1, AC1 allows us unbounded fan-in for both AND and OR gates, but there is a subclass of AC1 called SSE1. Okay, so AC1 actually stands for alternating circuit, SSE1 is semi alternating circuit. Okay, so SACI is the class of problems for which functions that have polycized order log to the power in depth circuits with bounded and unbounded OR gates. Okay. So, by definition it is a subclass of ACI and a superclass of NCI. Okay. So, this completes the proof of this theorem. So, what do we have here? So, what we have here is that, well, NC1 is in L, which is in NL, which is in AC1, and then of course, AC1 and so on. So, all of this actually can be shown to be in P, which is in NP. Okay. So, think about this. Okay. So, in fact, I will just give this as an exercise to show that NC is in P. Okay. So, given any circuit, any polynomial sized circuit which has log depth, polylog depth actually, it can be simulated in P. Okay. So, think about this. Okay. So, this completes the proof of this result. So, one more result I wanted to talk about, we can actually discuss it next time, but let me just state the result. Okay. So, remember those 4 relations that I showed. Okay. So, we showed that, well, NCI is contained in NCI plus 1, ACI is contained in ACI plus 1, and we showed that NCI is in ACI. Okay. But we can actually do a little better than that. So, what we can show is that, let me just look at the, okay, let C be a bounded Fanon circuit of size S and depth D, then C can be simulated by an unbounded Fanon circuit of depth D by, okay, K plus 1 and size, what is the quantity, at most 2 S D into 2 to the power C plus 1 for all C less than D. Okay. Sorry, not C, K. Okay. So, what we are saying is that there is a constant, not there is a constant, for any constant. Okay. So, you take any number, it need not even be constant. Okay. So, think of K as any number that is at most D. Okay. You can choose K to be whatever you like. Then what we are saying is that given a circuit of a bounded fan-in circuit of depth D and size S, I can actually reduce the depth by a factor of K. Okay, so, from D I reduce it to D by K, K can be anything for us, but of course, there is a blow up in the fan-in. So, now the fan-in can be unbounded and there is a blow up in the size as well. Okay, so, the size now becomes S into D into 2 to the power 2 to the power C. So, the size crucially depends, it kind of it is doubly exponential in C, but if I choose C carefully, then it might still work for us. So, as an immediate corollary of this, what do we get? We get that NCK is where? So, you can actually do NCK is in unbounded fan-in circuits of Pauli size and depth order of log n to the power k divided by, let me choose a different number here just to keep it so that there is no confusion, divided by log n. Okay. So, essentially what we are showing is that, well, we know that NCI can be done in unbounded fan-in circuits of Pauli size and depth log to the power in, right. But what I am saying is that I can actually do it even in log to the power in divided by log n. Okay. I can reduce the depth by a factor of log n. And how can I do that? What is the K that I will choose? Exactly. So, I will choose K to be log n. So, if I choose K to be log n, again this is not C, this is K. Okay. So, if I choose K to be log n, then I have 2 to the power 2 to the power K. What is that? That is equal to n. So, 2 to the power K is log n and 2 to the power log n is n. So, then I have n plus 1, S is of course polynomial, depth is of course bounded by a polynomial, so the size is bounded by a polynomial. So, the reason why I need to choose K to be log n is because I need the size to be polynomial, and now if K is log n, then clearly I get this as D, which originally was log n to the power I, and K is log n, which is exactly what I get. Okay. So, the proof is actually quite easy and it is not very difficult, but we will see this next time. Okay. Okay, so I will stop here.